All right, welcome everybody to Magic Virtual Showcase. We are the Memphis Area Geographic Information Council, and my name is Rob Winkler. I'm the new president of Magic for 2022, and I'd like to introduce my our new vice president for Magic for 2022, Michelle Field.
Hello.
Very quick about us. I'm a GIS analyst for DeSoto County, Mississippi. So I'm not even in Tennessee, but we are still the Memphis area. And I've been on the Magic board for about 5 years. And Michelle is with Smith Seckman Reed, or SSR, where I believe she's also a GIS analyst. And we are, if y'all were at our conference, you probably got a chance to see Michelle's presentation last November. We're also with Smith Seckman Reed, we have a little synchronicity here because our presenter today is also from SSR. So before we get started, just real quick announcement. Michelle and I are working on a lineup of presentations for 2022. We're hoping to have a mix of virtual and in-person events. We'd love to get back to those in-person events eventually, where remember we all used to get together at the Central Library in Memphis for third month, or usually the third Wednesday of the month. And we actually have that room booked for third Wednesday of the month, but we're going virtual for a little while things hopefully settle down soon. So there are some events already up on our website. We do have virtual events scheduled for February, March, and I believe even April. So those are already up there. And hopefully in the next few days or a few weeks, we'll have an announcement about our 2022 Magic Conference in November. Hopefully mid-November, just like we usually do, but look for an announcement coming about that. Okay, one other quick housekeeping note, annual memberships are up for renewal with a new calendar year. And there is a membership tab on the Magic website where if you want to join us by becoming a member and help support our programs, we do offer scholarship and all this professional development in our conference. And remember, your membership includes free admission to the annual conference, the 2-day conference. Currently, membership is $35 a year. And like I said, that includes the 2-day conference. As we get closer to the conference, that membership price does go up, usually starting around August. Okay, Michelle just put a note in the chat about if you have questions, please use the chat. And without further ado, I'd like to go ahead and introduce our speaker today, Katie McIndoe from Smith Seckman Reed. She's a civil engineer and a wastewater engineer with a civil engineering degree from Tennessee Tech. Please welcome Katie.
Thank you, Rob. I appreciate it. So like you mentioned, I'm a wastewater engineer out of Nashville, working for Smith Seckman Reed, SSR for short. So before we really get rolling, just wanted to say thank you guys so much for inviting me to speak to your group today. I promise I'll try and make this as interesting as possible. I know these online presentations can sometimes be a little dry, so I hope everyone is super pumped to talk and hopefully learn a little bit more about the riveting topic of how water models bridge the gap between GIS and real-life water systems. So, here we go. So before we really get rolling, I wanted to just have a brief overview of some of the major items that we're going to touch on today. We're going to talk about what a water model actually is and what people were even using before the water modeling software existed, and honestly, maybe in some cases, maybe still use. So what uses a water model actually has, how the water models are created, and then we're going to wrap it up with some case studies at the end where we've used a calibrated water model to help out some of our clients. In addition, at the end, I'll close out this presentation, and I have I have a water model pulled up. So if anybody has any specific questions about the software, we can always dive into that after the fact. So what exactly is a water model? The basic explanation is that it's a computer simulation of a water distribution system. So a well-calibrated model will actually mirror the system demands, the tank levels, the observed system pressures, and the pump operation of a city or a utilities water system. So a lot of the models that we've created and calibrated in-house at SSR will actually start with a city or a water district's GIS system. That geospatial relationship that's inherent to that GIS information that I'm sure most of you guys are familiar with working with allows us to create this powerful visualization of our client's water infrastructure. So when that geospatial information is combined with the functionality of this integrated modeling software, we can really visualize, one, where the water line is actually located, but two, how much water is actually moving through that water line in a given period of time. So there's a few different modeling softwares out there to choose from. All the snippets and whatnot that you'll see in this presentation are from Innovi's InfoWater. We use InfoWater Pro in-house, and it is actually an extension through Esri's ArcGIS Pro. So I get my toes wet with a little bit of ArcGIS, but I don't claim to know it super well. I'll leave it to folks like Rob and Michelle to do that. So before all of these different modeling softwares were created, distribution systems were evaluated through hand calculations or by use of Excel. As you guys can probably imagine, this process was super time consuming as it required multiple alternatives and iterations to get a good idea of what exactly is happening in a system over an extended period of time. So without understanding the main principles of these equations used to make the calculations in the model, the results that we export can be blindly applied without really knowing the full effect on the system. So even though we aren't doing these calculations really by hand anymore, the equations are still the backbone of the model and are very, very relevant in the results that we're able to export. The modeling software really just gives us a more holistic and a quicker approach when assessing an entire water system. This slide also gives me flashbacks to studying in college, so we'll move on. So with that really brief background of what a model is and where the models really derive from, we're just going to dip our toes into what the model is really used for. So as our cities and communities continue to grow, a lot of our local water departments, our utilities, cities are running into challenges that directly relate to water infrastructure, as maybe some of y'all know. Fortunately, the technology has continued to advance and water modeling software has developed so that utility districts have access to information regarding their distribution system. So that information is readily available for them to use and review on hand. This data also can provide insights to the health and condition of their equipment, how their system is operating and just their overall system in general. So really this model is a great tool for utilities and water departments to make informed decisions about their system and review any improvements that need to be made. So I know everybody can read the slide here, but one of the items we'll be going through is system optimization. So just a quick overview for each of these on here. A model can be used to easily develop and compare what we call what-if scenarios, such as identifying the most efficient pump operations, impactful incident responses, and also reviewing cost-effective design alternatives. So another use is the ability to develop what we call unidirectional flushing programs. I'm not going to dive too deep into that right now. We have a case study where we'll give a better overview of what all is involved in that. We can also prepare emergency response plans to help estimate the consequences of if a crisis were to happen in the system. We can also aid fire departments in developing ISO ratings for their hydrants throughout the system. So kind of helping them, distinguish maybe what color the hydrant needs to be and whatnot. We can also perform water availability studies for any new developments that are coming into an existing system, which kind of leads into, helping a client build a master plan. So building a master plan is where we can ultimately help them pinpoint weak spots in their system as the population grows and as their demand grows in their system. So this one can also sometimes help the development of a capital improvement plan and kind of helping the client pinpoint, I guess, giving them a roadmap of what things to expect down the line as growth continues. And last, which one we probably won't get too deep into at all, is water age and quality. So for example, we can measure the age of a water molecule and how old it gets from the moment it leaves a water treatment plant to where it may sit in the system for many days at a time. So if a utility is getting a lot of complaints on one area in the system of maybe like stale water or something like that, that's something where we can run this water age simulation and really pinpoint how they can address, that older water age. So before we can even really get started with using the model, we got to create it first. There's quite a few steps in creating a water model. The major ones are outlined on this slide. But we also can't really do a whole lot with creating the model until we have all of the data. But what data do we actually even need? Turns out it's quite a bit of data. And the data that we receive to create a model is really crucial to how accurate that model is going to be when comparing it to the live working distribution system. Usually at the start of a project, we try and tell our clients we're only as good as the data that's provided to us. So for example, if we're given GIS data that's 10 years old, that's obviously not going to be a reflection of what their system is today. More likely than not, they've probably made multiple system improvements and probably had some growth, and a lot has changed over that time. So anything that we create with that old data is not really giving them a good depiction of what's happening in their system right now. So that being said, updated GIS plays a huge role, as well as pump and tank information, which includes record drawings, pump curves, and just the overall parameters of the operations associated with the pumps or the tanks. We'll also request user billing data. So that's all of the water that's consumed in their system, accounted for by each meter or location. So then we'll know later on when we get to allocating the demands into the water model, how much we're exactly allocating and where we're allocating it to. We also request elevation data. So we need, usually we use LiDAR data with InfoWater Pro. We'll also request hydrant flow test and SCADA data, which we'll touch on those two pieces of data a little bit more whenever we get into calibrating the model. So once we have all of our data, then we can really get rolling with the meatier steps of the building of the model. So the next big step is transferring all of the GIS data and then reviewing the connectivity of the model elements created through that GIS transfer. I hope I'm not too much of a broken record, but I really wanted to drive home how essential GIS data is to the build of a model. The functionality of a water model is really only possible whenever we can create a one-to-one relationship established from a GIS feature to a model element. This means that for each water feature in the GIS database, a corresponding element is included/created inside of the hydraulic model. So how do we even create this relationship? You'll see on the screen that we have, I think it's up there, yep, GIS Exchange Cluster. So this is called the Gateway tool, which is where we're able to take the GIS information that's given to us, and then we're able to essentially map every quality that's associated with a pipe, a valve, a pump, you know, a meter, whatever it may be, and map that into the model. So once the model has been updated with all of this GIS information provided for the lines, the pumps, the tanks, valves, then we can go ahead and move on to the process of making sure everything is connected properly. So without everything being connected properly, then the model really won't run. You can't have a system with a bunch of broken pipes in real life. So same thing for a model, is if you don't have things connected, then it's not going to work. So this step of connecting everything is pretty involved and includes a lot of things I didn't plan on getting into, but if there's any questions about that later, I'm happy to answer them and bring up a live model to show you. So yeah, we won't spend too much time on going in on the connection there. So I touched on GIS transfer and creating model elements, but what are these model elements? So some of the water elements are listed here. We have junctions, pipes, valves, reservoirs, pumps, and tanks. Again, I'm not overly well versed in GIS, but I think most of these exist also in GIS data, mostly because we take that GIS data and we upload into the water model. So a junction, what does that represent? So a junction will really represent maybe your hydrants, your meters, your smaller system valves, and we'll use those to input our demands. And then once we run the model, then we'll look at those junctions to really take a closer look at, you know, what pressures are happening in the system. So for the pipes, that's a little self-explanatory. Pipes are brought in as pipes. You know, we'll bring in length and diameter, and then whenever we run a model, then we'll review the pipe element to look at velocities, head loss, you know, total flow going through the system. Valves, so you think of a valve, there's tons of valves throughout your system. But for the valve element brought into a model, we typically only bring in the larger valves. So this would be your pressure reducing valve or your pressure sustaining valve that's creating a boundary between pressure zones in your distribution system. Another major valve could be a flow valve, flow control valve, sorry, getting tripped up. So those are the three that we typically use. I think there's 7 total that you can use in this model, but we typically just use those 3. Reservoir, so I'm not sure if GIS really has a reservoir shapefile. However, in a model, you can't really run a simulation without a water source. So a reservoir in a model really represents either a water treatment plant or a connection to a neighboring utility that you may purchase water from. So you just have to have a water source in order to run your system. Pumps and tanks, those are both probably self-explanatory. Pumps are brought in as pumps, tanks are brought in as tanks. And that's good. That. So with the connectivity confirmed between all of those model elements, we could go ahead and move on to the next step, ensuring all of those elements have the correct inputs. So I think I mentioned putting the demands in, the elevations, and then the different attributes that go into, you know, making sure you have the correct lengths, the correct diameters for your pipes. Another example is, you know, you have a bunch of pumps in your distribution system and you have pump curves available for those pumps. So we'll need to take those pump curves and input those curves into the model. So then the pumps in the model actually match what's in the field. So backing up again to the data request around the billing data, we'll take that billing data of that water consumed over a period of time, and then we'll allocate that demand throughout the system. Ideally, whenever we make that data request, we also receive a GIS meter element that can be used for this step. So how we can use this billing data and this meter is we can join them as long as there's a cross-reference by a common customer account or another unique identifier. So whenever we make that link, we can tie that water usage to that meter and allocate the demands. Similarly with tank, you want to input diameter, overflow elevation, total height of the tank. So once you have all of those pipe attributes, pump attributes, all the demands allocated, all the elevations are correct, then that's when you can go ahead and start moving into the calibration process. The calibration process is a little more involved. It has 3 different phases. We'll have the static calibration, dynamic, and then extended period conditions. We'll go ahead and start with static, as typically that's where you want to start with. So when the flows are low in your system, that hydraulic grade line is really only set and influenced by a storage tank and then the pump station conditions. So because the flow through the system is really low at these times, the head losses that are typically associated with pipe friction are minimal and don't really impact any of the pressure readings. So because of that, we perform this initial round of calibration when that hydraulic grade line is relatively flat across each pressure zone. So this really allows us to make corrections in what we call the boundary elements if necessary. So what does that really mean? This is really a step where we can find any inconsistencies between the model and then the static field conditions. And that may be because we have an incorrect tank level in the model, maybe an incorrect valve setting, or maybe a valve is set to open when it needs to be set to closed. Or maybe we have the pump settings wrong, or maybe, gosh, we don't even have elevations associated with demand or with nodes. So we need to go back and address that. So that step is really where we calibrate that to kind of set those boundary element items. So once that's really complete, then we can go on and move to what we call the dynamic calibration or the high flow calibration. So in this calibration, this really allows for the impact of friction and other minor losses to be seen under a dynamic event or a high flow event. Typically, we'll simulate the system over a maximum demand day condition. So think of a hot day in August when people are using a ton of water. So that would be one of your maximum days of the year. So we're calibrating to that maximum demand day condition and then comparing our results to historical data from that same day in history. So this will allow us to really identify where the model calculations and then the field conditions differ under that dynamic event. So in this comparison, it'll generate a list of water lines where what we call C factor correction is required. The C factor is really, I guess, describing how rough the inside of the pipe is. So the lower the C factor, the more rough the pipe is, which leads to more head loss, which leads to more pressure loss. So we usually recommend, in order to kind of pinpoint what these roughnesses are going to be throughout the system, we'll ask our client to go through their system and perform what we call a 2-hydrant test. So they'll open one hydrant, measure the flow, and then at a hydrant upstream or downstream, they'll measure that residual pressure and take a recording. So we'll take that flow and that pressure and we'll put it into this little screen that you see here. Was a snippet from what we call the Calibrator app within InfoWater Pro. So we'll take that information, we'll input it in here, and the model will generate these new C factors that will ultimately help us match the pressures that should be seen throughout the system. So we'll recommend all of those locations where we feel are best to calibrate. And so the field fill data from these hydrants will be really just used to better fit the model closer to that dynamic event. So once we kind of have all of those C factors dialed in, that process is a pretty iterative process. You can go through the same area multiple times and change your C factors a bunch of times until you get it right. So it's a little bit more of an abstract, a little bit more abstract than the static calibration. But once you get all of that into place, then we can go ahead and move on to what we call the extended period calibration. So in the extended period calibration, we typically try to calibrate the model to a 48-hour time period simulation in the model. This will help ensure that the model accurately reflects how the system is operating over that period of time. This also ensures that pump controls, demand allocation, demand curves are all reflective of actual conditions in the field. So this would allow clients to look back and use the model for projecting maybe a system response to various instantaneous changes at various times of the day. So if you have a, say a large spike on your pumps in the middle of the day and that's not expected, then they know something's not right. Anyway, so in the calibration, in this step, we use the historical pump and tank SCADA information under a 48-hour window, and then we compare that to the 48-hour extended period simulation that we run, and we compare the model results to the actual SCADA data. So in this slide, we have a couple of examples where we've calibrated to one tank that we have, and then a pump station that we have. So we're really tweaking the controls to try and dial in and try and make these match as close as possible. And you can get pretty dang close in the model, which is pretty helpful moving forward. But typically we're looking at tank levels, pump run time, suction and discharge pressure at pump stations, and then also pump flow to kind of complete this calibration. So once we've received this good fit over an extended period of time, then that model will almost be ready to start using. So I say almost because we have one more step, and that's creating various scenarios. So a lot of scenarios don't come online until a client reaches out for something to be looked at. However, usually whenever we initially build a model, we'll start out and create an average day demand scenario, maximum month, and a maximum day. So that average day is just over 365 days. What did the person average use over that time period? The max day, I think I mentioned like a day in August when, it's hot, people are watering lawns, people are using a lot of water. That max day may fall in August or September on a hot day. So we'll go ahead and create those just so we have a baseline for any analyses that we have moving forward. So now that we've covered how to make the model, what the model is, I'd like to go ahead and circle back and talk a little bit more about the uses and then go through a few of the case studies where we found successes with using a calibrated model. I don't think we're gonna, well, I know we're not gonna touch on all of the examples that we touched on earlier, but we have 5 here that we thought would be beneficial and maybe interesting to talk a little bit more about. So with that, we'll dive a little bit more into system optimization. Just to recap from before, the model can be used to review various system operations to identify, pump operations, response actions, and then review different design alternatives. So with the ability to create these various scenarios that we just talked about, the model can be used to easily switch between different scenarios to fine-tune operations under certain system conditions. So for this example, we're taking a trip up to Bowling Green, where Bowling Green Municipal Utilities, or for short, requested that we review the construction of a new 1 million gallon tank to see if it would improve, one, their water quality, and then two, also the pressure that's in their south pressure zone. So this new tank would be replacing an existing tank. The existing tank was not really providing consistent pressure throughout the pressure zone, and it also was not providing as fresh water. So I think we touched on that water age before. So this, what we call tank turnover. So the tank really wasn't turning over, meaning water was not coming out of the tank as often as it should and not filling up as often as it should. So we created a scenario to review this new tank to see if there would be any benefits to the construction of it. Part of the exercise included taking the other tank offline. And so on this slide, you'll see a southern red circle. Let's see, the southern red circle right here, that represents, or it's circling where the existing tank is that's proposed to be taken offline. And then this northern red circle is where the new tank was proposed. To also make this scenario successful, we had to modify the existing controls of an existing pump station that filled the existing tank that was proposed to be taken offline. The pump station, I guess, it was now going to be modified to fill the new tank in lieu of the old one. So after we ran the scenario with all of these modifications in place, we were able to find that the pressure in the pressure zone was going to be consistently higher with the new tank. In addition, another benefit that we found is that the pump station is now filling the new tank would be operating at a much more efficient spot on its pump curve. So because of these findings through their calibrated model, we were actually able to recommend they move forward with the design of the new elevated water storage tank, and then also help them operate one of their larger pump stations on a little bit more happier point on their pump curve, and ultimately saving them more money through energy cost. Another example for uses on a model is unidirectional flushing. So we're going to stay up in Bowling Green for this example as well. So again, I guess back in 2020, BGMU reached out to us asking if the model could be used to help them develop what we call a unidirectional flushing program. So for those of you not familiar with flushing, and sorry for those of you who are, water departments, utilities, cities, they perform routine flushing to, one, they can verify hydrant operation, to evaluate, the available flow at the hydrant. And then three, and I guess one of the more common things that we think of on our side in engineering is, scouring the pipe to remove sediment, any sediment buildup, to ensure that they're delivering the highest quality of water possible to their consumer. So there's a couple different methods that are used to achieve this. One is called traditional flushing, and the other is this unidirectional flushing. We're not going to really spend any time with traditional, so all of this kind of circles around the unidirectional flushing and how we can use the model with it. So unidirectional is where valves and hydrants are closed so that scouring velocities are ultimately increased to remove debris and that dirty water from the distribution system. In order to do this, we use the model to create flushing zones that have multiple flushing sequences identified within that model. So each sequence consists of a pipe segment. Sometimes that segment is in a loop. So for example, this snippet in here, this orange line that you see is a sequence that's ran where we're trying to scour that pipeline, and all the blue pipelines in there are all the previously flushed lines. So we're flushing this water to the left and then down and then out that hydrant. So really the goal is to flush all of the sequences so that a flushing crew is really out there for one day. This really allows for, the crew can be out there one day do their work, and then begin to reopen / close all the valves that were modified to isolate pipe segments during the flushing. So this avoids any issues with people complaining about not being able to get water and whatnot whenever those pipes are closed. So once all of these sequences are established, modeling software can be used to export the flushing, what we call the flushing journals, for the field crews to utilize whenever they're implementing this new program. So again, this is a snippet from the model, and it's actually from one of the field journals. I think quite a bit of stuff is cut off from it, but hopefully that gives you a good idea of what some of the export can look like from the model. So another benefit from the model is, and one of the more common things that we run into is, looking at the impact of a new development would have on a new system. So in Pigeon Forge, we primarily perform availability studies just by request. So because the city is known for the mountains and all the tourism, the growth in the city is a healthy mix between commercial and residential, which makes each availability study pretty unique. I know we've looked at some stuff for Dollywood, and then obviously, all the different cabin developments that have gone up there. The reviews we complete for them typically consist of, I guess we'll start with looking at existing conditions in the system without the new development. So then we can really get a good idea of, okay, what is the pressure at this connection point without all of these new demands in the system. So once we have a good idea of, what's the pressure right there? What are the local tanks or pump stations doing before this even comes online? How are those operating? So then whenever we input the new development, we can go back and kind of compare all of the changes, see what impacts the added demand is from that new development. Part of this review, we also do a fire flow availability. And so we'll apply a fire flow demand in the development, usually at the highest point, and then run the model and see if the system can supply water up there under those certain constraints. And so if it's not able to, then we're able to make recommendations on how they can do that and how they can actually achieve for this this development to come in place. So that actually happened up in Pigeon Forge. There was a development that came online, and whenever we put it into the model, we found that it completely drained one of the tanks up there. And so we said, oh, that's not good. We can't be draining a tank just from this new development in general, and then also in fire flow. So what can we really do to fix this? Luckily, they have a different pressure zone boundary right near. And so we were able to install a new pressure sustaining valve that can open and allow flow and higher pressure to come into that area and ultimately fill the tank and provide those peak demands that happen. Another example is emergencies. So I think I touched on, coming up with an emergency response plan. This wasn't so much coming up with a plan as it was just addressing an emergency. So Jackson Energy Authority contacted us. I think this was a couple years ago. They had some major rains that came through and exposed one of their 12-inch water mains. So they called and they said, okay, hey, we're gonna need 3 weeks. We're gonna have to take this down, close it off. Can that area even handle this pipe closed? So we were able to go back into the model and review this area with that pipe closed over I think it was either a 7 or 14-day simulation. And so what you're seeing on this slide is the tank that we looked at that's nearby, that's ultimately providing most of the pressure. We were able to see, yeah, it does dip a little bit, the pressure does. However, after 4 days, it really stabilizes and they really won't run into any issues when providing flow into this area. So that was, where our model came in handy, where they need a quick answer. We're able to give them something relatively quick by just popping this in the model and seeing what would happen. Last, one thing we're going to touch on is just going through master planning. So I think I touched on this earlier, but models can be used to help develop master plans and also update master plans. So I think back in 2014, we created the master plan for Jackson Energy Authority. We utilized the model to, one, taking those projected population growth and those projected demands and putting it into the model by different scenarios. So when I say different scenarios, we looked at the existing day, 5-year, 10-year, 15, 20-year. So we were able to really pinpoint where those weak points would happen as time went on. So we use the model to do that and then summarize for that into a master plan. Similarly, we just wrapped up a master plan update in Brentwood. Their system is a little bit different as they don't have a water treatment plant, but they purchase water from Harpeth Valley Utility District and Metro Water. So in a fire flow event in the northern part of their area, they really rely on that Metro Water connection to provide adequate fire flow. So they asked us to really take a closer look into that and see if there was another way that they could meet these fire flows without relying so much on the connection. So that was something that we were able to incorporate into the master planning. And I actually believe that's the last example I have. So I can open it up to questions, and just a reminder, I do have a model open, and if anybody's interested in looking at something specific.
Awesome. Thank you, Kate. And before we get to questions, just want to apologize. I don't know if anybody else calls you Katie, like I did when I introduced you, but
Oh, I don't mind.
I meant to say, I was worried about messing up your last name, and sure enough, I messed up your first name.
Hey, it's no worries. I actually used to go by Katie, so I respond to it.
All right. Well, that makes me feel better. If any of y'all have any questions, feel free to tap on your screen on the little microphone icon and just speak up, or just type it in the chat. I guess while we're waiting, one question that came to mind for me is, and I'm really not a water expert at all, I'm just a GIS guy, but that scenario you talked about where they were building that new development, or they were proposing to build a new development and it was going to drain the whole tank. Kind of made me think, are municipalities constantly needing to do these kind of models before they approve a new development to make sure they're not going to have to build a new tank or something like that?
I would definitely recommend that, especially, if it's a larger development, like a lot of Pigeon Forge things, they have these massive cabin developments that come online, or I think I mentioned Dollywood that we did, but they built this, what they call their Dreammore Hotel, which that just pulls a lot of demand from the system. And so with something like that coming online, we would definitely recommend doing one of these reviews prior to them coming online.
And is it typical where do these municipalities have this water modeling capability in-house and people knowledgeable like you, or do they typically contract out for?
I've seen a combination. I know some utilities, they do it in-house. For example, First Utility District in Knoxville, they do all of their modeling in-house, but in the same vein, Pigeon Forge, they contracted out to us to kind of update and keep a hold of for them. So a healthy mix, but I would say more oftentimes than not, that work is contracted out, and if they wanted the model, we could of course give it to them as it's their property, but they usually ask us to operate it for them.
Okay, thanks, Kate. I see a question in the chat. There's a couple now. One from Matthew Davis was the first one. Are you seeing that? What is the most common issue you run into while trying to use GIS data for modeling?
Yeah, so one thing I really didn't get into is, I think I mentioned the connectivity. So trying to think of the easiest way to describe it without getting into too much of the weeds. So when we get this GIS data, so you have a pipe, let's say this is the pipeline and my watch is a junction. A lot of times the GIS data will provide one consistent pipe, even though there's something that's actually connecting right here.
Oh, I definitely know what you mean. Yes.
Yeah. So what we have to do is we'll essentially break that connection and create two new pipe segments. So
Yeah, I'm sorry,
go ahead. No,
I was going to say in municipal GIS, we have to do the same with roads, because anytime roads have a junction, it's got to be a junction. I see one of my colleagues, Scott Trapolino, is on this call. He's with City of Olive Branch, and he inherited one of those situations like where you're describing, where junctions weren't really junctions and didn't connect or didn't have a pipe broken at the junction.
Oh yeah, so I would say that's the biggest one, because we have to ultimately export all of those, I guess, pipe breaks. And so whenever we make those exports, then we ask our client to go back and update their GIS, which, going back to that, what I called the one-to-one relationship between GIS data and those model elements, making sure that unique identifier, everything's still consistent with that identifier. So when that's broken, when that pipe is broken, you're breaking that one unique identifier into two new pipes. So, yeah.
Yeah, I feel like good GIS people should know to do that already, but apparently that's not the case always.
Yeah, it's getting better, honestly, but yeah.
And we have another question from Serena Hostetter. Are you still able to use GIS features and tools within the water modeling software, since the software is an add-on? If so, what GIS tools do you use the most?
Definitely can. So I'll pull up the model. So I think, is my screen still sharing? You guys can see that all right?
Yes.
Okay, cool. So we still have all the same tabs and ribbons in ArcGIS. For me, I typically just use the selection tools the most often. And to be honest, also the bookmarks. So definitely can use them. All of those capabilities are still there. Another way that we use them is creating nice looking layouts for our clients to look at information in a prettier way than, this massive map. So yeah, can definitely still use the ArcGIS ribbon and all the commands in there. Let's see. So Michelle, you asked, do I have any experience using Fathom AFT? I do not. No, I do not. I'll be honest, I'm not entirely sure what that is. I'll have to look it up and brief myself on it a little bit more.
Okay, yeah, and we also have a question from Sean Anderson. What is a typical time frame to create a water model?
So I would say that it varies. It varies by size of system and also by the quality of data that were provided. So for Bowling Green, for example, they had everything readily on hand. So theirs, I would say it was about 4 months, I believe it was, to create it and get it calibrated and working. But it can range, I would say, 3 to 5 months, typically.
With that 3 to 5 months, does that include the whole initial GIS feature creation part?
So whenever you say GIS creation, do you mean them creating their GIS or us taking the GIS and creating it in the model or uploading it into the model?
The first, where the GIS people create the features, or is that additional beyond the 3 to 5 months?
Yeah, I would say that would be additional. So if somebody doesn't have a GIS system at all, and they want one,
I didn't mean that.
that adds quite a bit of time.
No, I didn't mean that.
Yeah.
I just meant creating the features in the data set.
I gotcha. Yeah, so that would include that time then.
Any other questions? Oh, we got one from Tyler.
What sort of information do you normally get from utilities billing data, and does it translate well to GPM data? So typically we receive in an Excel format. So we'll get, I'm trying to think of the best. We'll get their usage over a year of time. And over that year of time, it's also, that demand is also associated with each meter. So it's a massive file. So yes, sometimes it's given to us in a different, like in gallons per year. And we have to dial in a little bit more. But we can usually get it to gallon per minute demand pretty easily. Yep. So we use the closest node method. I think there's a few other methods that we use. There's like a polygon method where you could, say, I mean, this is exaggerated, but say all this area is in one polygon and you can allocate demand into that polygon. You can also allocate it to the nearest pipe. So that flow will, say you have a meter right here, that flow will go to that nearest pipe and then be split between those two nodes. So if it's 10, you'll have 10 GPM that's allocated. You'll have 5 GPM here, 5 GPM here. But typically we do the closest node process. It's usually the most accurate. I think they're going to roll out, hopefully new things within the model. They'll have more capabilities. Sorry, I don't know if anyone saw that question, but it's any thoughts on Autodesk recent acquisition of Innovise? Well, Autodesk, 1, is becoming a powerhouse, and 2, I think just having the backing of AutoCAD, they're going to be able to, maybe even add more apps that are useful to us that we can ultimately help our clients have more capabilities of, reviewing their system more. But also, I mean, changes in licensing and, stuff like that. But overall, I don't see if there's going to be all that much change.
All right, so we have about 5 minutes left. Does anyone else have any questions?
Okay, last chance. All right, well, awesome. Kate, thank you so much. That was really informative. Really appreciate your time.
Yeah, no, again, thank you so much for having me. I really appreciate it.
And oh yeah, and then we're getting thanks. So it doesn't look like any more questions. So, all right, well, thanks y'all, everybody, for attending. And our next webinar will be, I believe it's February 16th. That will be a presentation about the GISP certification. So if that's something you're interested in, definitely want to tune in for that. All right, again, thanks everybody. Thank you, Kate. And this is Memphis Geographic Information Council virtual showcase signing out. Y'all have a great day.
Thank you guys. Take care.
Bye.